In this one, we've got a heat exchanger type problem. It says it's an air conditioning system that's shown. We've got air that's flowing over tubes carrying the refrigerant 134A, which is basically Freon. So you'll see here we show the air coming in. That's the little orange area. And then we've got the refrigerant going through these tubes. Now the air is going to enter with a volumetric flow rate of 50 cubic meters per minute. Temperature is 32 degrees Celsius. Pressure is 1 bar. And then down here it exits at a temperature of 22 degrees Celsius and a pressure of 0.95 bar. So notice the temperature has decreased and the pressure has also decreased. Now the refrigerant enters the tubes at a pressure of 5 bar, and it gives you the quality here. It's 20%. And then it exits over here with a pressure of 5 bar and a temperature of 20 degrees Celsius. Now we are going to ignore heat transfer, the outer surface of the air conditioner, and then we're going to neglect the kinetic and potential energy effects. We're also going to say steady state conditions, and we want to find mass flow rate of the refrigerant. So it's in the tube. Notice the units, kilograms per minute, and we want to find the rate of heat transfer in kilojoules per minute between the air and the refrigerant. So let's get started on part A. Now this is mass flow rate, so pay attention, we had steady state. So for mass flow rate, we know that m1 dot is going to equal m2 dot. So this is dealing with air. And those are going to be the same, so let's just call it m air dot. For the refrigerant, we'll have m3 dot equals m4 dot, which is then mr dot. So now we've got that. Let's go ahead and get another equation, because obviously we don't have enough information here. Another equation we have that has m dot in it is the energy balance equation. So let's look at that. Now our control volume is going to be this whole thing. So think of the rectangle as being the boundary of our control volume. So keeping that in mind, our energy balance equation is going to be 0 equals q dot minus w dot plus m dot for the air times h1 minus h2. And then you're going to have the same thing for the refrigerant. So I have plus mr dot times h3 minus h4. Alright, so now we've got that. And I can cancel out the kinetic and potential terms, so that's what we are left with. Now what we want to do, let's see what else we can simplify here. Q dot goes away. Q dot, if your control volume is this rectangle here, that would be basically the heat transfer from the air conditioning system to the surroundings. So it tells us to ignore that. We don't have any power generated here. We're not inputting any power, so that goes away also. Now with that, we can solve for mr dot, which is what we're looking for. So mr dot is going to be the mass flow rate of the air times h1 minus h2 over h4 minus h3. Alright, so now we got that. Then what we need to do next, we still can't solve for anything. These things could be found in the table, but we need to find m air dot. So let's look at that. So m air dot is going to be AV over V. We'll have that. Now with this, we can use the ideal gas, and we can rewrite that as AV1 times pressure 1 over R times T1. Now AV1 that was given, that was 50 cubic meters per minute. So we have that, and then P1 is our pressure, that's 1 bar. And then we want R times T1. R bar, you have 8.314, put that over 28.97, that's your molecular weight. And then we get kilojoules per kilogram Kelvin. Temperature is 305 Kelvin. Now notice we got bar, we got kilojoule, we got all that stuff. We need to do conversions here. We'll have the 10 to the 5th Newton per square meter per bar. And then finally 1 kilojoule per 10 to the 3 Newton meters. And then that's going to give you 57.12 kilograms per minute. So that is our mass flow rate of the air. Now that we've got that takes care of this. Now we're left with these enthalpy values. Now H1 and H2, you're given temperatures. You can find those values in the table. You're going to go to the ideal gas table. So let's just put from the ideal gas table. And again, that's table A22 if you're using the same table as I am. You're going to get H1 is 305.22 kilojoules per kilogram. And H2 is 295.17 kilojoules per kilogram. So that takes care of that. Now when we go to H3, we aren't given a temperature. Remember, for ideal gas, everything's based on temperature. We don't really care about the pressure. So now you're going to have to use your equation that uses quality, because quality was given. So for this one, we're going to have H3 equals HF for the values at 0.3 plus X3 times the difference between G and F, points G and F, so that'll be that FG3 entry in the table. That'll give you 71.33 plus 0.2 times 184.74. And your units, after you do the calculations, will be kilojoules per kilogram. That gives you 108.28 kilojoules per kilogram for H3. Now, again, anytime you're given quality, that should typically lead you to this equation. And finally, 4.4, we've got pressure and temperature here for this refrigerant. Now, you need to figure out exactly what you've got there. So if you look in the tables, if you look up this pressure in the saturated liquid table, what you're going to get is at 5 bar, so come over here to saturated refrigerant, go to 5 bar, temperature there for the saturation point should be 15.74. We are above that, we're at 20, so that means we have superheated vapor. So go to the superheated vapor table, look up those values, so this pressure temperature combination, and then you can get H4. And H4, what is that going to be? That's going to be 260.34 kilojoules per kilogram. Now we've got all of our H values that we need here. Let's pause equation 1. Now we can plug everything into this. And then we can get our mass flow rate of the refrigerant. We need M air dot, that was the 57.12. It's kilogram per minute. And then put all your enthalpy values in here. So at 305.22 minus 295.17, put that over the H4, so 260.34. And then let's subtract H3, which is 108.28. And all of those are kilojoules per kilogram. So all the units there are going to cancel out. So this is going to leave you with 3.775 kilograms per minute. So there's your answer for part A. All right. Now for part B, we want the rate of heat transfer between the air and the refrigerant. So this time, instead of looking at this rectangle as our control volume, what we want to do is let's just look at the refrigerant. So the pipe for the refrigerant is going to be our control volume. And that, when we do our equation here for energy balance, then our Q dot term will be the heat transfer rate between the air and the refrigerant. If we did this whole rectangle, Q dot would be the rate of heat transfer between the whole system and the surroundings, which is not what we want. All right, so let's go down here. Let's write out our equation. We're going to have 0 equals Q dot minus W dot plus M air dot. And then let's go ahead and multiply by H1 minus H2. Now, as I was writing that out, I just realized we're looking for the Q dot between the air and the refrigerant. You have two different ways of doing that. You could either use your MR dot equation and use H3 and H4, or you could have a control volume that just contains the air. So either way you want to do it. So I'm going to go ahead and use M dot air because that's I already have it worked out that way. So let's switch to that. If you wanted to do it the other way, you would just have MR dot and then you'd have your H3 and your H4. Okay. And you should get a similar thing. So now that we have this, we can go ahead and plug in our numbers. So Q, let's call this air, dot, is going to be the mass flow rate of the air times H2 minus H1. Notice W dot goes away because we are not generating any power. We don't have a power input. Plug in our numbers. We get 57.12 kilograms per minute times 295.17 minus 305.22. And that's kilojoules per kilogram. That gives us negative 574 kilojoules per minute. All right. So now you've got that. So we've got a negative value. So negative Q dot means we are losing heat energy. Okay. So there you go. Alright guys, now if y'all want, y'all can test it out, do it the other way, use the mass flow of the refrigerant, switch your enthalpy values, see what you get.